from Trinidad, and thank you for coming to our session today. I am very excited to be part of this Lubrication and Reliability Virtual Summit. Very excited because I'm seeing technology moving in leaps and bounds and allowing us to still connect while we are a bit disconnected. So very happy that you could take part out of your time today to sit with us and get to know a bit more about lubrication, which is why we're here. So very glad that they did this summit virtually. Our borders are still closed in Trinidad at the time of this recording. So if we were to have this in a physical space, I would not have been able to attend. So very glad for the opportunity. Today, I'm going to be talking to you a little bit about lubrication degradation mechanisms and what you should know, because there are a lot of things that are not directly available in the public domain. And one of the things that we wanted to do is to really get the information out there to make sure that professionals like yourself can have access to this so that you can better help the reliability of your plants, because that's totally important. And just for you to understand what's going on with your lubricants, with your equipment, with everything that plays a bigger part and plays a bigger role in this. A little bit about me. Well, I said it before, I am Sanya Mathura, and I am the Managing Director and the Senior Consultant at Strategic Reliability Solutions Limited. We are based in Trinidad, and we actually offer the services of training, and that's one of the aspects that we take very seriously. Since we are a heavily industrialized nation in the Caribbean, I wanted to make sure that our guys and our ladies are prepared for what happens in the field and to become experts in their own rights, to make sure that they can identify issues and troubleshoot and be able to understand what's going on with their equipment and how it helps their reliability. So you'd see us promoting courses like root cause analysis, basic failure analysis, reliability engineering, RCM, and even PMP. So all of these sort of form parts of the holistic development of a professional within the industry. And we're so glad that we have great affiliates that help us to bring this information to Trinidad and globally as well. My background is actually in my BSc is in electrical and computer engineering, which is very different from reliability and lubrication. But after I worked in that industry for about 2 years, I started working with a global oil and gas supplier and in the lubrication industry. So I've been in the lubrication industry for about 8 years. And what I've realized is that a lot of times the lubricant gets blamed. It's the first thing, no matter what, they blame the lubricant, first thing that they do. So I wanted to help people to understand that even though your lubricant may fail, it's because of the environment that it's in. And being able to understand why it's failing actually helps you to help your equipment and to make sure that you have more uptime. So I did my master's in engineering asset management, and I recently got my MLE from ICML, and I actually wrote a book, and it's called Lubricant Degradation Mechanisms, a complete guide. And part of this content that we'll cover today is actually covered in the book, of course, in more detail. And the book is actually going to be out in November, later this year, so stay tuned for that. And let's get into our agenda for today. So there are 4 main things that I want to focus on. The first being the definition of lubricant degradation. Now, we have to be able to define what lubricant degradation is. We have to start there. So we're just going to follow a sequence of events. So we're going to define what it is. We're going to get the methods for identifying lubricant degradation. We have to verify these things. So we need to do lab tests. And of course, we have to know how to deal with degradation. So let's jump straight into it. Now, this is actually a picture of a diesel engine. You could tell because the oil is so dark and murky. So it was an inspection that I did on a diesel engine for one of our transport providers in Trinidad. And of course, we can tell that the lubricant has been degraded. So what exactly do we mean by lubricant degradation? And it's a term that, people struggle with a lot. But before we even get to lubricant degradation, what are the functions of a lubricant? Now, when we think about it, and we think about this logically, if we have a function, if your lubricant is not providing the function that it's supposed to be doing, then it's failed, in a nutshell. So ideally, if we follow that train of thoughts, if we define the functions of a lubricant, we can then understand why it has failed providing any of those functions. Most people have different definitions of the functions of a lubricant. These are just 5. There are so many more that are out there. So the 5 that I have on the screen would be just to reduce the friction. That's the main function of a lubricant. Improve the efficiency, minimize wear, distribute heat, remove contaminants. And if you are thinking about hydraulic oils, you're actually thinking about transmitting power. So that's another function of a lubricant. If you're looking at it from the oil analysis perspective, a lubricant is a conduit of information. So if it does not provide any of those functions, essentially it has failed. So we understand when a lubricant has failed, right? So that's one step. Let's think about actual degradation. Now, degradation happens throughout the service life of the lubricant. If it doesn't happen, then something is wrong. And I've had people tell me about their engines, and they've put the oil in their engines and it's still golden after about 6 months of using the engine. Something is wrong there. Something is definitely wrong there. When an engine works, it produces dirt. And one of the functions of a lubricant is actually to remove those contaminants and keep that dirt suspended. So that is one of the reasons that oil actually gets a darker color. So it has all the dirt suspended in it, if we're talking about engine oils. So if your oil is still golden after 6 months of using your engine, something's wrong. It's not providing the function. But the purpose of a lubricant in terms of degradation is that it will degrade over time. It has to degrade over time. That's one of the functions of it in a way. But understanding that from the moment you put the lubricant into your equipment, you will start having degradation occurring. But there will be a point at which the degradation is to a level that you no longer serve the function. The function of the lubricant is no longer served, and it can't protect the system. That's where we have an issue. So by understanding that the degradation occurs throughout the life, however, we need to know our limits with that. Ideally, there are 6 modes of degradation, lubricant degradation. There are some people who argue that there are 3, but I'm sticking with the 6 because these 6 actually produce different types of things. Some people try to group it together using environmental classifications. So because of that, certain degradation mechanisms may fall under each other. But ideally, there are 6, and they are oxidation, thermal degradation, microdieseling, electrostatic spark discharge, additive depletion, and of course, contamination, which happens no matter what. We have to try and reduce contamination as much as possible. But I will go through these with you and help you to identify the different mechanisms. Because by identifying them, then you can understand what is going on with your system, what we can do to help, and actually bring your system back to life in some cases. So when we talk about oxidation, oxidation is the one that gets the most amount of the most amount of blame, I want to say. So every time we have some sort of varnish or something goes wrong, the immediate effect is that somebody says it's oxidation. But there is a difference between oxidation and some of the other different characteristics. So when we talk about oxidation, oxidation is actually the addition of oxygen to your base oil. And I want you to remember that we're talking about addition to your base oil, not necessarily additives. So when it attacks your base oil, the things that are usually formed will be like your aldehydes, your ketones, hydroperoxides, carboxylic acids. Why do you need to know this? If you have a system that has one of the processes running through it, let's say it's an ammonia system, and you have carboxylic acids being produced, more than likely it's going to be reacting with your ammonia because that's an acid and a base. And that's what's going to be causing your oxidation. So by understanding that you have oxidation occurring in your system, then you can know what your results would be in terms of your byproducts, and you can act accordingly. Now, understanding that these are some of the products that may be produced when oxygen is actually added to the base oil helps us because there are different stages in which oxidation could occur. So, for instance, perhaps your lubrication system is just now at the first stage, which is initiation. And of course, initiation is where you have your free radical being produced. And like the name suggests, it's radical, so it needs friends. So it actually goes on to the second stage where it's propagation and it gets a lot more free radicals. And because we have this group of radicals, they go ahead and they wreak havoc throughout the entire lubricant. And they continue doing that oxidation process until they've deleted all the antioxidants within your oil, and then they start attacking your base oil. So your antioxidants, they're like your defense mechanism, and your radicals, they go after them and they try to deplete them as much as possible. However, if you could stop the free radical from being produced, basically stop oxidation before it started to attack your system. So understanding the different stages can help you to verify and to know where in your system you want to start with dealing with oxidation. But we will get into dealing with oxidation a little bit. Now, some of the results that we get from oxidation, you get varnish, you get sludge. And one thing that you'd realize is that you start getting an increase in viscosity. Your base oil breaks down because it's attacking your base oil. Your additives get depleted, and all your anti-foaming properties are gone out of the window. So those are some of the things that you can look for when you're looking at your results for oxidation, when you're analyzing what's going on with your system. Now, thermal degradation is one that is often confused with oxidation. They go together. A lot of people get them mixed up, but they're actually very different. And one of the main things and the main differences is that with oxidation, you actually need oxygen. With thermal degradation, you're looking at the thermal cracking of a lubricant, and your temperatures actually exceed 200 degrees Celsius. With oxidation, you don't have a cap on your temperature. So in thermal degradation, what happens is that your molecules become shared because you're telling your lubricant that we're gonna crack you. Let's think about this like in those distillation towers. They're actually exposing the lubricants to excessive amounts of heat and pressure. So your molecules are gonna start dropping off and it's gonna polymerize. And the difference, one of the main differences between your thermal degradation and your oxidation would be that you actually get a decrease in viscosity with your thermal degradation. Oxidation increases your viscosity. With the process of thermal degradation, it's actually a bit different. So when your oil becomes cracked, small molecules, they start coming off of your chain of your oil. And two things can happen to them. Either they're volatile and don't leave any deposits, which is good in a way because we don't have as much cleanup, or they could condense and they have dehydrogenation, or you could actually produce coke as a final deposit. So that's one of the main differences in terms of the results of what are produced by thermal degradation compared to oxidation. And I just wanted to compare that so that you all know the differences. With oxidation, it requires oxygen. With thermal degradation, you have to have temperatures over 200 C. Oxidation, you increase in your viscosity. Thermal degradation, you decrease. Oxygen produces your varnish and your sludge. Thermal degradation, you have lacquer and carbonaceous deposits. Because remember, it's really attacking your base oil. So your base oil is really composed of carbon molecules, in essence. So you're gonna start seeing those deposits. Now, we're going on to microdieseling. With microdieseling, people say it is a form of thermal degradation, and it's also known as compressive heating. And what happens with that is that you actually have air bubbles that are trapped in the system. So think about when those bubbles are passing from low pressure to high pressure. What actually happens on inside is that you have localized temperatures, and those temperatures could go in excess of 1000 C, which is a lot, quite a lot. And that bubble interface actually becomes carbonized. And when that becomes carbonized, that is when we start seeing your oil darkening, you start seeing change in color. And it's different because even though this is a form of thermal degradation, when the oil darkens, the carbon deposit produces the carbon deposits because of oxidation. So we can't exactly say that this is thermal degradation. So that's why I have it singled out as its own unique degradation mode. And the difference with microdieseling is that it can either have a high implosion pressure or low implosion pressure. Now, what that means is that depending on the pressure, that would actually dictate what happens in your system. So if you have a high implosion pressure, then the products that you're gonna get will be incomplete combustion. So that's what you're looking for. If you had a low implosion pressure, then you're looking for stuff from like varnish, you're looking for coke, you're looking for tars, you're looking for resins. So it's a difference in terms of the pressure that the oil is actually exposed to, or rather that bubble. So by understanding that, we can know if we have high pressure to low pressure systems, if it is that the flash point will always be low for microdieseling, so there's no risk of a fire there. But getting the different types of products that are formed helps us to understand what's going on in the system, what the entering air is actually being subjected to, so that if we understand that, we can know what we could change in the system, what needs to be done. Now, the other one is electrostatic spark discharge. Now, this one is very interesting because we have static electricity everywhere. Now, imagine if you had that static electricity inside at a molecular level in your oil. Now, I know usually like if I'm walking around and I touch a handle, a door handle that is metal, I may get a shock, and that's not nice. So if that happens on the inside of your oil, it's going to be worse. And when you have static electricity at a molecular level, and you have dry oil passing through tight clearances, which just makes me think about hydraulic oils right away. It's going to be a point where all of your static electricity builds up so that it forms a spark. And now this spark could actually have temperatures in excess of 10,000 degrees C. Now, we know with lubrication, once it goes over 60 degrees C, we have, for every 10-degree rise, we have a half, oil life is halved. So imagine if it's at 10,000 degrees C, we just killed our oil. basically. So there are steps to ESD, of course, there are steps to all of them. And what happens is that your static electricity first builds up and it produces that spark. And once it produces that spark, we have these radicals being formed again. And of course, you know, they love friends and they will continue to polymerize your entire lubricant until it gets to a point where you just have a lot of varnish, you have a lot of sludge. Some of it may remain in solution. Some of them may drop out, they may plate out. But understand that you have ESD occurring helps you to identify what mechanism you need to put into place. Because even though you have polymerization of the oil, it's not oxidation. It's because of ESD. So that's why this is separate, it's a separate mechanism. And while we talked about thermal degradation, microdiesel, and electrostatic spark discharge, I want you to know some differences. Some people, they group all of them under the same thing, under thermal degradation, but there are differences. There may all be forms of thermal degradation, but there are differences to note. And one of the main differences would be the temperatures. So if you're looking at thermal degradation, anything over 200 C. Microdieseling, it must be over 1000 C. Electrostatic spark discharge over 10,000 C. And then you have a difference in terms of what deposits are being produced. So just be aware of that. They are not all the same. If you have thermocouplers in your equipment, that helps in terms of narrowing down which one you have going on in your system. And then, of course, by the different products that are being produced. If you're looking at additive depletion, now, when we think about additive depletion, most lubricants, they are sacrificial in nature, especially your additives. The reason that they are put into the oil is actually to protect the oil, to protect the equipment, but they have to be present so that they can work against the different, I want to say, attackers in the oil. So if you have acids in the oil, they want to fight against them. So for additive depletion, what we need to understand or what we need to gather is the type of additive. And when you have your deposits, you can actually do either organic deposits or inorganic deposits. So your organic deposits could be so with your organic deposits, you either have organic or inorganic. Usually with your organic deposits, those are like your rust and your oxidation additives. And your inorganic deposits, that could be like your ZDDP, which is used to reduce wear, very important for your gear oil systems. And they may not react with anything else in your system, which is good because they just drop out and they stay there. That is good, that's helpful as well. But understanding the actual type of deposits helps you understand which additive has actually dropped out or it has been depleted. Another degradation mechanism would be contamination. Now, people don't think that this is a degradation mechanism, but by understanding what contamination is, we can understand that it leads to different types of degradation mechanisms. So any foreign material that enters your lubricants and that can be used as a catalyst for degradation, that is contamination as a degradation mode. And usually we classify those based on metals, water, and air. And what we've realized is that a lot of the times your contamination, degradation can lead to different modes of degradation, usually in the form of oxidation, thermal degradation, or microdieseling. So that's just a bit of an introduction with the different modes and the different types. Now, for the interesting part, the lab tests. Now, knowing which lab tests you need to administer for the different degradation mechanism actually helps. So you're not just doing a million different lab tests and trying to figure out what is going on. if you have an idea of how the process works or how the degradation process occurs, then you can figure out what's going on with your system and do your own troubleshooting before you spend a lot of money in the lab and do tests that they're not going to give you results that will help you to verify which type of degradation mechanism is going on. Now, oxidation is usually one of the first bad actors that are called out almost all the time. And what I just want to reiterate is that if your oil has degraded to a point where you're now doing the testing, you may not get as much valid results as you would have if you started doing your testing from the moment the oil went into the sump. And with oil analysis, trending is very, very important. So if you don't have a base to compare it against, then you're kind of shooting in the dark. You're saying, well, I don't know what happened in my system before, but something happened now. So we have nothing to compare it against. And while you may want to compare it against what your oil supplier, your OEM has, the conditions that the oil would have been under would have been pristine conditions before it would have been in any equipment. So by using that as your base to compare against, it's not the best thing to do. However, if you are putting new oil into a sump, I would always recommend 24 to 48 hours, then take a base sample. That's your base sample, and that is representative of what is going on with your system. And it's important to know what's going on with your system because your system is gonna be different from somebody else's system. So it's very, very important to have your baseline sample and then compare it against that. And different types of equipment would have different schedules for doing their different sampling and to do their comparisons. If you're looking at oxidation, some of the tests you want to definitely check out would be your acid number. If you start seeing that increase over like a 0.3, then something's going on. If you start seeing rapid changes in color, definitely something is going on. And a lot of people, they underestimate the use of FTIR, and that's Fourier transform infrared. And the thing about FTIR is that each substance gives off a particular signal. So imagine being able to verify what exactly you have going on in your oil. So FTIR gives you the presence of those insolubles. So it's a great test to use. Now, MPC, ruler, and RPVOT, those are great for oxidation, but not in isolation. And I say that because I've seen and I've done tests before where your MPC value was within the good region, less than 15, green, nothing being present. But your RPVOT values were less than 25%. So what that says is that your antioxidants are being depleted, but it's just not showing up in the MPC. So your deposits are actually remaining in solution. And that is scary. But at the same point in time, by doing the two tests in tandem, it helps us understand what's going on. And I know that some plants may have budget restraints, and these tests are a little bit expensive, but it's always a good idea if you are checking for oxidation. If you can do at least 2 of the tests, you can do the MPC and the RPVOT together. If you have the budget for a little bit more, you can do the ruler, which helps you to understand your phenols and amines, and that gives you a better understanding. And you can also throw in your QSA tests, but it depends on if you have the budget. And while we don't mention the viscosity test as a verification for oxidation, it should still be done. But if your viscosity increases, that doesn't necessarily mean that it's oxidation. It could be a million other things. But it's good to have that in addition to all of the other tests that we have here. So it's a great thing that you should have. Definitely make sure if you're doing oxidation that that is done. And now for your thermal degradation. Now remember, we kept saying the differences between thermal degradation and oxidation. And one of your main differences would have been your viscosity test. Now, if your viscosity decreases to about 5%, then, and we start seeing rapid changes in color, we confirm with FTIR that we have carbonaceous deposits, you have thermal degradation definitely going on there. Also verify if your viscosity decreases, that it's not a contaminant that's decreasing your viscosity. So definitely something to keep in mind when you're looking at microdieseling though. Now, the first thing I want to do with microdieseling, remember this is the entrainment of air moving from one part to another part of your system. So the first thing you want to do is do a visual inspection of your components and check if cavitation is present. If you have cavitation present, you definitely probably have some form of microdieseling going on there. That's even before you get to the lab. And if you want to confirm, you can do your FTIR and your QSA test and just look for the different types of byproducts. So you're looking for, if you had a high implosion, you're looking for soot, tars, sludge, and of course with low implosion, you're looking for carbon insolubles such as coke, tars, or resins. So that's what you're going to be looking for and the test you have to do for microdieseling. On the other hand, if you have electrostatic spark discharge, and I mentioned earlier that this usually happens with hydraulic systems or even with turbine systems. And what a lot of the guys say is that they start hearing crackling every time they walk past the equipment. So that is another indication that you may have electrostatic spark discharge going on. And a great way to confirm this is by looking at your filters. Your filters, if you have ESD occurring, your filters are going to get these burnt patches and you're going to start seeing your clogged membranes. So that's a great indication that you have ESD going on before you even get it to the lab. To do your confirmation, of course, you do your ruler test because your antioxidants are going to be depleting like crazy. Just because you have that going on, you check for your dissolved gas analysis and you look for acetylene, ethylene, methane. These are what are usually produced with ESV. And of course, you check for your varnish, check for your sludge, check for your insoluble materials. FTR and QSA, great tests for those. And if you're looking at additive depletion, remember we spoke about this earlier, where different additives would deplete at different rates, and we don't know which exactly would be depleted. But some tests that you can use would be your FTIR and your QSA. Again, FTIR is very, very good for this. And some labs actually have the color that would be associated with different additive types. So it's a great indication if you see a change in color and you note the color change. So sometimes if you see like an orange or you see a red, you'd have probably some different type of additive being depleted and it's been showing up in the oil. Of course, your ruler and RPVOT, they are great for understanding the presence or the absence of your antioxidant additive because those are perfect for that. And you have your QSA to determine if you have some insoluble materials. With contamination, the first thing we can tell usually is just by a visual inspection of the sample. Most times, if it's contaminated, we can see it right off. And this would be the ingress of any foreign material. Sometimes a change in color actually helps. It could be that the oil turned green because there was a green coolant involved that contaminated it. Or it could be that the oil turned into a different color, that is, perhaps it was a turbine oil, which is mainly clear or a lighter color. And the oil was a slightly golden color. It could have been contaminated with a gear oil. So color is important, but definitely get it to the lab check out what exactly they have going on the inside there. Now, it's great to know the different types of mechanisms, to know which lab tests to perform, but we need to know how to deal with degradation. And that is critical because that's the main question people ask, what do we do now? We know we have all of this going on, what next? So one of the main things that you have to do is understand your equipment. So understanding your equipment, determining the applicable tests, interpreting the results, and of course, implementing your different measures. And all of these, we can't have a standard cookie cutter approach for this because they change depending on your organization, depending on your budget, depending on what is critical to your organization or not. So when we look at understanding your equipment, now what I like to do is actually classify this in terms of critical, semi-critical, or non-critical. If we had a failure in the past and oil analysis, helped us to identify that the failure was occurring, then people may say, okay, let's do oil analysis on every single piece of equipment. While that sounds nice, it's not necessary if it is that we have equipment that are non-critical, in that they have a secondary, they have a backup. So oil analysis on a basic level may be fine, but we don't want to perform RPVOT, which is a bit expensive, for a non-critical component. So dividing your assets into critical, semi-critical, and non-critical helps you to understand where you want to put your focus on. And criticality can mean different things for different people. So if we're looking at the fleet industry, a critical piece of equipment could be a truck that has to do a job for a client that could only be done at that time. Or it could be a truck that if it doesn't run, the business doesn't get a profit or it's contracted out. On the other hand, if you're looking at like a manufacturing industry, criticality there can mean if that component goes down, the entire plant goes down. So it depends on what criticality means to you and how you classify your equipment for just understanding it and then assigning your different lab tests to it. So now if you know what it is, what you're working with, you have to look at your applicable lab tests. And these are just some of the basic ones that I would say you can do like on a routine, monthly, twice in every like 2 months, every quarter. It depends on your budget, of course, and what is critical and what is non-critical. These are just very basic ones to help you identify if you have degradation actually occurring. So viscosity is clearly very important. If you start seeing changes of plus or minus 5%, we want to monitor that for sure. If you have the presence of any sort of contaminants like water or fuel, definitely something we need to look at as well. If you're looking at your TAN, and in some cases you may need to do TBN, if you start seeing increases of your TAN of 0.3, or you start seeing your TBN going on by about 50%, then we want to be monitoring those. And then, of course, when you do your spectrometric analysis, you're going to look at your concentration of your additives, your metals, your contaminants. So these are just very basic ones that you want to look at. And I wanted to give you an idea of some sort of results when you start interpreting your results, because this is the part that gives a lot of companies some trouble. When they get back the results, they don't know how to interpret it. And they need to understand, like, what does it mean? So if we saw where there was an increase in viscosity, your acid number spiked, it was a dark color, but there was no water present. So usually if you have water present, that's immediately contamination. So you're looking at the types of modes that could be represented by some of these conditions. And one of the major modes that could be presented would be oxidation. And a great way to verify that would be doing your elemental analysis. Elemental analysis helps a lot. Your RPVOT, your ruler, MPC, that helps you to understand if you actually have oxidation occurring. And then by doing these tests at different frequencies, you can actually trend the rate at which your oxidation is occurring so that you know what's going on with your equipment. I want to say how much time you have, but what's going on with your equipment, what that means for you. Can you schedule downtime? Is it okay for you to schedule downtime, or can you not afford to schedule downtime? So this is what helps us to understand. Now, what if you had a decrease in viscosity? You had a dark color present, but no fuel. Usually, if you have fuel present, your viscosity goes down immediately. It goes. So some of the modes that could be present with a decrease in viscosity, a dark color, would be thermal degradation, microdieseling, electrostatic spark discharge. And you want to try and verify that based on what you've observed. So if you inspect some of the components and you see a burnt membrane, you know, it's probably ESP. If you see cavitation, it could be microdieseling. And when you're sending your samples off, it's critical that you note whatever you found on your components, because the lab, when they're doing their analysis of it, they're going to be checking for these things. And if they know that you've seen some sort of cavitation, they're going to be looking more heavily on microdieseling, and it helps them to narrow down the test that they will have to do. So always good things to do when you're sending off your samples. Give a note. Say what you've seen, say what you haven't seen. And while you may think that it's not helpful information, it's actually very, very helpful. And it gets them to understand what exactly they want to do the test on. And while we know after we've done that, we have to implement measures. And you can't just do cookie cutter again, because it depends on your system and depends on what degradation mode you've seen and how the degradation mode has actually occurred. And one of the first things a lot of people say, they say go straight to chemical filtration. And when you do chemical filtration, that sort of removes different things from your oil. But what I would say with that one is definitely you need to analyze your system first, ensure that that is the best way forward, and then employ chemical filtration. Usually people use that when they have oxidation problems. In some cases, and you definitely need the OEM approval for this, if you adjust your clearances and your bearings and some of the other smaller areas, this helps to reduce your temperatures. And why we want to reduce temperatures is that that's where we have thermal degradation occurring. That also helps with oxidation. So by just adjusting those clearances, you actually increase your flow rates of your oil. So you decrease your temperatures significantly. But you need OEM approval for that. So that may take a bit of time. Another way that you can do in terms of dealing with degradation would be your residence time. Now, there are a couple of times where your oil flows through your system, and especially in the instances where you see you have microdieseling occurring, that's where your air gets entrained, or you have the tuning of the oil. And if you have tuning of oil, it could mean that your oil is getting into your system. It's not having a very long residence time for the air to release with the antifoaming properties. So a great way to do this would be increasing your residence time of your oil if you can, decreasing your flow rates, but OEM approvals, always get your OEM approvals. And another way you can do this is through kidney loop filtration. Now, with your kidney loop filtration, a lot of people, they just run this filter through their oil and they just put it on the side. And it helps remove a lot of the contaminants. And if you use antistatic filters, it's going to help you with ESD definitely. So it's going to remove some of the static that you have going on with ESD. Now that is great. That helps a lot with that. So it depends on what you want to implement, and then it goes back to which degradation mechanism you're trying to prevent. And also goes back to what is going on with your system in terms of that degradation mechanism. So knowing the mechanism is great, verifying the mechanism is good, but we need to understand your system and then implement a measure. Because what works for your system may not work for another system, or it may need to be tweaked a bit. So we can't always do cookie cutter for these. And that's why it's critical you work with your OEMs and you make sure that they are definitely on the same page with you, and you can work with them to actually solve what's going on with your equipment. And that is it from me today. And I really hope that you learned something. If you take away anything from this, then let it be that there are different types of degradation mechanisms, and we need to be aware of all the different types of them, and just use wisely, and understand what's going on with your equipment. Always go back to what's going on with your equipment and your system. So thank you so much for your time today, and I hope you have a great remainder of your session. Bye.